Chew. Alrighty. Structure 2.1. So this is the ionic bonds. It's relatively easy to me, and it's pretty straightforward. So first thing we have to know is how ions are formed. Turn on TNT. How ions are formed. So generally, and I think this goes through chemistry, in your periodic table on the left is metals. On the right is nonmetals. And a pretty simple definition that will help you actually understand this is that metals are elements or atoms that I think they donate, right? Yeah, donate electrons, and nonmetals are atoms that accept electron. It's a really general definition. If they ask you, is probably what you do. But essentially, what happens in an ionic bond is that a metal bonds, let me write this better, bonds with a nonmetal. So let's take sodium and chloride, Cl. So in the valence shell, which means the most outer shell, sodium only has one electron, while chlorine has 1, 2, 3, 4. Right? So in an ionic bond where this is a metal, which is on the left of the periodic table, and this is a nonmetal, which is on the right of your periodic table, they bond. And the sodium kind of gives the electron to the chlorine and forms NaACl. So now the sodium has a full valence shell because it donated its one singular electron now in the valence shell, and chlorine has now a full valence shell because sodium kind of gives it to chlorine. Okay, it's pretty simple. This is something you have to know too, is what are cations and anions. Cations are your metals, and anions are your nonmetals. What they do is that it has a positive charge, and here it has a negative charge. And they form when they ionize. You know, cat and an. What my teacher taught me, she kind of said cats are good, so they're positive, and then anions are negative. Okay. But so metals are your cations and anions are your nonmetals because, well, the Na, it loses one electron, right? At the start, the Na was neutral with its one electron, but then it kind of lost this electron, so its charge now becomes positive because electrons are negative charge, right? So if you think about it, 0 and you plus a -1, no, you subtract the negative, not plus. You get 1, right? So this will kind of be the charge because it was at neutral here, and then you took away the negative charge, which is the electron. Same thing with your nonmetals. You start at 0 and you add a -1 because you're adding the electron in, which you'll get -1. So it'll be a negative charge. So this is your anion and this is your cation. Let's draw that. Let's make it better. Next thing. There's something to keep in mind. Sometimes IB will ask you questions that you probably might not know about, like properties and stuff. It's always, I think I mentioned in one of my other videos, I'm not sure if I uploaded it or not, but it's always good to have a common one in mind. Always have something that you feel comfortable with. So I like to use NaCls for my ionic bonds because it's just table salt, right? If it asks you properties, which we'll talk about later, I'll go into it, but you can just think of the properties of table salt and you would know. Moving on. Let's see. Next thing you have to know are binary ionic compounds. Let's write this better. What this kind of is, it kind of just is an ionic compound. The definition is that is composed of ions of two different ions composed of two different elements. So, as we just said, NaCl, table salt. So, this is a binary ionic compound. Or let's say lithium sulfide, LiS. Or magnesium oxide, MgO. These are all binary ionic compounds, okay? And why this is important is that sometimes you have to know how to name them. And you name binary ion compounds is you say the cation first, so the metal, with the anion, so non-metal, but you end this with the IDE. Okay, so let's do some practice. So if I have lithium and sulfur, which I would probably already spelled it before, and they bond and form LiS, lithium and sulfur. What you want to do is that you can think about it. Pause the video, think about it. That's enough time. What will happen is that you'll get lithium, so your metal, and your name of your anion, Sol, and you end with the IDE, so lithium sulfide. That's how you name it. But yeah, that's really all you have to know. Definitions of an ionic bonding. What is an ionic bond? So this is something you have to know. It's the actual definition. Is that I'll write it down first. Remember this because they might ask you, and this is a pretty accurate definition. But it's the force of attraction between two oppositely charged species. Species essentially is ions. The word species comes out a lot. Just think about like animals, different species. Drink some water. Yeah. So you can kind of deduce this definition because we know that it's cations. So it's a cation bonding with an anion. They're bonding together, right? So this is a positive charge and this is a negative charge. And if you have a magnet, it'll help you kind of understand it better. But essentially, you have to know that negative and positives attract each other. Positives, positive, or negatives, they repel each other. If you use a magnet, if you put the north and south side, it'll kind of stick to each other, right? But if you put the north and north side, it will start repelling each other. It's kind of happening the same thing here, but on a molecular level. But essentially, yeah, just know this. The force of attraction between two oppositely charged species. Did I miss anything? Let's see, let's continue. And, let's just name this part ionic compound stuff. Ionic compound stuff. So first thing you have to know is that it's neutral. Okay, the charge is neutral. So if we go back to what I was talking about in the sodium chloride, this is a positive charge, or you can write +1 charge, and this here is a negative charge, -1 charge. So if you add them together, so -1 plus 1, you would get 0, thus making it neutral, right? So ionic compounds are neutral. No, go to this in a bit. Actually, no. Yeah, let's start with this. Yeah, it's kind of going into the pluses and minuses a bit more. Is that your metals are always positive charged, therefore they're cations, right? So, although there are non-metals that could be positive ions like NH4 plus or H plus, generally, because we talked about how the left is your metals, right? So your left would be group 1, 2, and 13 for some reason. Yeah, 13. Yeah, 13. So the when they ionize and they become stable, right? It becomes a +1, +2, and +3. +3. Yeah, generally that's really it. Group 13, you just look at the last number. Same thing goes, and you guys probably learned this in structure 1. I don't remember. But essentially, you're just looking at the last number of which group it's in. So 1, it has 1 valence shell. I mean, 1 valence electron. 2 valence electrons. 3 valence electrons. And I mean, if you think about group 18, then it has 8 valence electrons, right? You don't have to know about this yet, but transition elements, so it's like the middle chunk of your periodic table. But they can, although they ionize and they're called transition metals, they don't necessarily have to be metals depending on various things like temperature and pressure and all that stuff, but that's not for now. But yeah. What else? Negative ions or non-metals, anions, they are in groups 15 to 17. So what you want to think about is like this. Let's say I have element X, it's full, and okay, so this has a full valence electron and it's stable. The whole point that elements or atoms bond is that they want to be more stable. They don't like to be crazy and shit. So they would try to find this. So let's say if it has 2 missing electrons from being a full octet, then what would it want to do? Of course, it will want to take in electrons because that is the simplest. It's simpler than losing 6 electrons. They all take energy to do things, right? It's easier. And what they would do is that they would go the easier route, the lazy route. So they would take in. So as we just talked about, you can kind of link this together. It has 6 valence electrons. So what group will it be in? If you said 16, good job. Group 16. So what you can kind of infer to this is that they would do the easier thing. So let's say if it was in group 15 with 5 valence electrons, then of course gaining 3 electrons would be easier than losing 4 electrons. And you might spark the problem where what if there is only 4? It's perfectly in the middle from being a full octet. Well, I can kind of do whatever it wants. Okay. That's my understanding. It does whatever it wants. But usually you won't be asked about this. And yeah. And it kind of looks about what is bonding with this. So maybe like a carbon. It depends on what it's bonding. Not a big deal. But yeah. What did I say? Oh, polyatomic ions. I hate this. Polyatomic ions. What you can see, poly, multiple, atomic, atoms, and ions. Okay, so it's composed of multiple atoms. Another name for it is compound negative ions. I haven't seen it. I haven't seen anyone use it or in an IB question, but good to know. The more you know, right? So there are generally form of generally negative ions. They're generally negative ions, but some could be positive. Some are positive. So, for example, NH4. It's a positive one. You'll learn it in reactivity 3. But a couple you need to know. Actually, you have to know. Yeah, you have to know for IB. And really, I never really memorized it. I'm gonna be honest with you guys, but I wish I did, because it's really good to know. They come up really often. But just spend some time memorizing it. If you can't memorize like me, then just start doing. If as you go on with the course, you'll get more familiar with it. But anyways, NH4, which is ammonium. Hydroxide, which is OH minus. Nitrate, which is NO3 minus. Hydrogen carbonate, which is HCO3 minus. Carbonate, which is CO3 minus. Sulfate, which is SO4 2 minus. And phosphate, which is PO4 3 minus. Okay, so the reason you have to know these 7 is that first, they come up really often, and if they want you to name something, you'll want to know this, right? So, let's say you have NaOH. You don't say it's sodium, oxygen, hydrogen, right? It sounds kind of dumb. Stupid to say that. So, what the actual name would be, it'd be sodium hydroxide, because the OH comes together, and it's a polyatomic ion, which we just named here, so it's sodium hydroxide. It's easy as that if you memorize it, but generally, I feel like as you get throughout the course, you would be familiar with these and you will actually understand them and actually know how to name them, but you might struggle a bit for your little test. Next thing is ionic lattices. Okay. Ionic lattices are essentially lattice structures. So I think about it as a Rubik's Cube. I'm Asian like that, but so let's use different colors. Easier to see. Okay, I'll just draw it to this. Like this, right? So the green is positive. Or your cation ions. And blue is your negative anions. Okay, and I drew a little plane because I can't draw 3D shapes. I'm not artistic like that. But it's just kind of this shape, but like goes down. It's like a cube. And what you have to know is that they'll always attract to each other, right? There's the bonds. I can't zoom in them. Bond. These are electrostatic forces. There are electrostatic forces holding them together because it's a positive and negative charge, right? The word electrostatic is also a really good word to know. If you want to put in definitions for ionic bonds, it makes you sound smart, and sometimes the mark is that you have to mention the word electrostatic. Like there's no like talking out of this. You're like the IB mark team will sometimes just force you to have this in or you don't get the mark. But yeah, they're evenly distributed and neatly arranged in the lattice. So with this in mind, this is another property of ionic mods. Oh, my ionic compound stuff is filled. But essentially, because they're put in this cube structure, right? They all have bonds coming out of each other and they all have strong forces that attract them to each other. What we can infer from this is that they have high boiling points or high melting points. This is what we can infer from them. If you think about it, it's salt. NaCl, salt. It's an ionic compound. And have you ever seen those videos of people like melting salt? That's really it, right? You're melting salt and it takes really high temperatures to melt it, to fully melt it into like this molten way. It's because it's an ionic bond, which creates a lattice structure. And it's really hard to kind of break those bonds because they're so stable. You have to break all 4 bonds to kind of continue it. And next thing, I think it's that it's brittle. I think it's brittle. Because if it's like in a lattice structure, right? If you kind of push one layer off, you would force a positive, it's better. You will force a positive on a positive, which repels each other. And so, it kind of doesn't like each other. So if you put force on it, it's going to kind of shatter it apart. So they're also brittle. I'll add on to this later. I have to check the notes too. You're not gonna like this. Lattice dissociation enthalpy. Enthalpy. Why is this even here? Where can I write this? I'm trying to write here. Lattice. Lattice dissociation enthalpy, which is denoted as delta H lat. The definition of this is standard enthalpy change. Standard enthalpy change that occurs on the formation of ions. Formation of 1 mole of gaseous ions from the solid lattice. So what this really means is that if you start off with a lattice, like that, right? It's a cube. I'm bad at drawing, okay? Don't judge. But you start off with a lattice, and you're kind of breaking it apart. You're breaking this lattice down to form cations and anions, which then requires energy to break, okay? And that's really the lattice dissociation enthalpy. Dissociation, breaking down lattice, is your lattice structure. And it is always endothermic. Meaning that your delta H, your enthalpy change, is always greater than 0. Because if you... I have to go back to that little... Here. Let's do this. right? I'm using minuses and pluses just for the sake of it. And their bonds here, you don't give them energy to break them. Oh, actually, yeah. They need energy. If you put enough energy here, you're kind of pushing it on this bond and it kind of disappears. So that's why it needs energy to break. It doesn't release energy to break, okay? Because essentially you're breaking the ions, right? So it needs energy. Oh. Okay. Let's go back to this ionic compound stuff. Let's really fill this in. So we talked about high melting points and brittle. Oh, this is a good word to know. I've encountered a couple questions on this. Is volatility. Volatility is talking about how it vaporizes, right? How easy it is to vaporize or melt. And so if it links back to the high melting points. High melting points means it's not volatile. It's not easy to kind of boil. And they are soluble in water. Meaning that NaCl, well, just go back to think about salt, right? This is where I said having something as common in life really helps because it's the exact same thing. If you put salt in water, you're not gonna see salt particles if you mix it enough, right? So what really happens at a molecular level is that it becomes Na plus and Cl minus. Just kind of floating around in your water. So that's really it. That's what it means by soluble. It can break down easily when you put it in water. Conducts electricity. When molten or in solution. This kind of goes back to the point. Let's say I'm in a cup and there's water here, right? So I have Na plus and Cl minus kind of moving around. Oh, what the hell just happened? What really happens is that the way electricity gets conducted is the movement of electrons. If you did B.5 in physics, you should know this. Electricity is essentially the movement of electrons, because they're all pluses and minuses, right? There's kind of like electrons kind of moving around too. And because of these delocalized electrons, they can conduct electricity. Same thing then when it's molten, it's not put in water, it's just melted itself. So it kind of does the same thing, right? It has ions that freely move around and they kind of bring the electrons around and conducts electricity. But then when it's solid, so let's say ACl. When solid, the electron doesn't go anywhere, or the bonds don't go anywhere. Your NaCl is just kind of there, so it can't conduct electricity. Again, just think about salt. That's really it. What else? Oh, and that's it. This is it for the Ionic model, S2.1.